Number of states in a spin system. A system consists of capital N spins 1/2, each having magnetic moment mu0 and is located in an applied magnetic field B. The system is of macroscopic size so that N is of the order of Avogadro's number. The energy of the system is then equal to minus n prime mu0 b, if n denotes the number of its magnetic moments which point up and n prime which point down. Calculate for this spin system the number of states which lie in a small energy interval between E and E plus delta E, where here delta E is understood to be large compared to individual spin energies. Delta E is much greater than mu0 b. Okay, so let's start with this part A of the problem. Now we note that in an n spin system where we have n moments up and n prime, which is capital N minus n, down, the energy of the system will be equal to minus net number of up spins n minus n prime, each having a moment mu0 b. So it is minus magnetic moment dot product with the magnetic field. Since the magnetic field is pointing up, we're looking at the net up moment, which is minus 2n minus capital N mu0 b, because n plus n prime is equal to capital N. So for n prime, we substitute capital N minus n. So corresponding to this energy, there will be a certain number of accessible states. The number of accessible states not for an interval, but for the scenario where we have energy E, you see we have a one-to-one correspondence between E and N here. So one E value is corresponding to one N value. That is equivalently saying having N moments up would be given by combinations of capital N objects taken n at a time. So this would be equal to capital N factorial divided by n factorial capital N minus n factorial. However, what I'm interested in is not the number of accessible states for a certain energy, but for a certain energy interval. So omega E, which is the density of states multiplied by the energy interval delta E, in which the density of states is not changing appreciably. So we have the density of states equal to d phi dE, the number of accessible states for energies less than E, derivative with respect to E. So now you can see that I can write this as omega E is equal to d phi dN dN dE multiplied by delta E. So I can equivalently write it this way. So it's quite clear that I'm interested in d phi dN, the number of accessible states for a certain n range, multiplied by delta E divided by dE dN. So you will basically realize that you can write, since the energy of the system is minus 2n minus capital N mu0 b, we can write n as, so we can isolate n and we can write it as minus E over 2 mu0 b plus capital N over 2. So so that 2n is equal to minus e over mu 0 b plus capital N. So we can isolate it this way. So this basically tells us that dn de is minus 1 over 2 mu 0 b, or de dn, you can read here, is minus 2 mu 0 b. Any change in the n value, an incremental change in the n value, results in an incremental change in energy in units of minus 2 mu 0 b. So since this energy interval that I'm interested in, delta E, is much greater than mu 0 b, we can calculate the number of n values, up moment values, that will satisfy, that will correspond to energies in the range e to e plus delta E, as delta E, the energy interval, since we have a change in the energy of 2 mu 0 b for each n value change, dE dN absolute value. So this is going to be delta E divided by 2 mu 0 b. So when I have a change in the n value, the energy is changing in increments of 2 mu 0 b. So this is telling me basically the number of n values I can have to satisfy the energy requirement, that the energy will fall in this range e to e plus delta E. So, and for each n value, I have combinations of capital N, taken n at a time, accessible states. So therefore I can obtain the number of accessible states when I have energies in the range e to e plus delta E as combinations of capital N objects taken n at a time, multiplied by the number of different n values that I can have, delta E divided by mu 0 b. So since capital N is a large number here, so basically we are neglecting the variation in the combinations. So when n changes by an amount, by 1 or 2, by small amounts, the number of combinations doesn't change appreciably. So here we have an approximation basically. So the number of combinations multiplied by the number of values that n can take to satisfy energy falling in this range. Okay, find an explicit expression for ln omega as a function of E. Since both n and n prime are very large, apply the result. We have Stirling's approximation to calculate both n factorial and n prime factorial. Show thus that to excellent approximation we have this expression where E prime is defined as E divided by mu 0 b. Okay, so let's work on the natural logarithm of this number of accessible states, ln omega E. This is ln capital N factorial minus ln n factorial minus ln n prime factorial, which is capital N minus n factorial, plus ln delta E divided by 2 mu 0 b. So using Stirling's approximation, ln omega E is can be approximated as capital N ln n minus n. Stirling's approximation. This is Stirling. And for n factorial, I can do the same thing. Minus n ln n. It would be minus n, then it becomes plus because of the minus sign up front, plus n. And similarly, minus n prime ln n prime plus n prime. And then I have the last term, ln delta E divided by 2 mu 0 B. And n is equal to n plus n prime is equal to capital N. So here I have n plus n prime, which is capital N. So I see that this is going to cancel with these two. So I have a minus n and plus n. So this will be equal to now capital N ln capital N minus n ln n minus n prime ln n prime plus ln delta E divided by 2 mu 0 B. And now I'm going to define E prime as E over mu 0 B, because that is suggested in the problem statement. And E divided by mu 0 B is actually, if you go back to this energy here, it was E divided by mu 0 B is basically minus parentheses n minus n prime, or n prime minus n. So basically, or n prime minus capital N minus n prime to n prime minus n. So we can write it this way. So basically, for n prime, I can use E prime plus capital N over 2, and for n, which is capital N minus n prime, I can use capital N minus E prime plus capital N over 2, 2n minus n, it will become n minus E prime over 2. So substituting these for ln omega, then I can write ln omega as capital N ln capital N minus, for n I substitute n minus E prime over 2 ln n minus E prime over 2 n ln n minus n prime I substitute n plus E prime over 2 ln n plus E prime over 2 plus the last term ln delta E divided by 2 mu 0 B. Okay, so if we continue this calculation, we can write this as ln omega E is equal to capital N ln capital N minus 1 over 2 capital N minus E prime, and then I have natural logarithm of 1 over 2 plus natural logarithm of n minus E prime, and then we have minus 1 over 2 n plus E prime, parentheses natural logarithm of 1 over 2 plus natural logarithm of n plus E prime, and then we have natural logarithm of delta E divided by 2 mu 0 B. So this becomes capital N ln capital N minus 1 over 2 n minus e prime times ln 1 over 2 minus 1 over 2 n plus e prime ln 1 over 2, and then we have minus 1 over 2 n minus e prime ln n minus e prime, and minus 1 over 2 n plus e prime ln n plus e prime, and then we have the last term ln delta e divided by 2 mu 0 b. So this becomes n ln n minus n ln 1 over 2 because we had 1 over 2 n's in the summation, so there is 1 here, 1 over 2 n, there's 1 over 2 n here, and 1 over 2 n here. So this becomes minus capital N ln 1 over 2 minus 1 over 2 n plus e prime ln n plus e prime minus 1 over 2 n minus e prime ln n minus e prime plus ln delta e divided by 2 mu 0 b. So the other term we had was plus 1 over 2 e prime ln 1 over 2, and then we had minus 1 over 2 e prime ln 1 over 2, so those disappeared. So in this expression we had this term, and then we had this term 1 over 2 e prime so there is a minus and there is a plus here, so they cancel. Okay. So this is going to become capital N. So since I have capital N parentheses ln n divided by 1 over 2, so these two will become capital N ln 2n, and then I have minus 1 over 2 n plus e prime ln n plus e prime minus 1 over 2 n minus e prime ln n minus e prime plus ln delta e divided by 2 mu 0 b. So we can write eventually for ln omega e, so that's what we're doing here, ln omega e, is basically capital N ln 2n, and then we have minus 1 over 2 n plus e prime ln n plus e prime minus 1 over 2 n minus e prime ln n minus e prime so e prime is e over mu 0 b. So in this approximation we can basically neglect the last term because the last term will be small. So to an excellent approximation we can write this equation. So we have neglected this last term here because it's small. Okay, so for part C, make a rough sketch showing the behavior of ln omega as a function of E. Note that omega E does not always increase. The reason is that a system of spins is anomalous in that it has not only a lowest possible energy minus capital N mu 0 b, but also a highest possible energy plus N mu 0 b. On the other hand, in all ordinary systems where one does not ignore the kinetic energy of the particles, there is no upper bound on the magnitude of the kinetic energy of the system. So there is an upper bound, highest possible energy here, which gives us an anomalous behavior in the number of accessible states as the energy increases. So in order to sketch this, first thing I want to note is that if you look at ln omega E and ln omega minus E, where E prime was basically E divided by mu 0 b, remember, so it was defined here. If I change the sign of E prime to plus or minus, I will get the same thing. So ln omega of minus E. E prime was E0 E divided by mu 0 b. So it's symmetric around zero energy. And for energy equals to the minimum and maximum values, capital N mu 0 b, what would E prime be? E divided by mu 0 b would become plus or minus capital N. So for E prime is equal to plus capital N, for example, if I look at ln omega E, it would become capital N ln 2n minus 1 over 2 n plus E prime becomes 2n ln 2n, and then I would have minus n is 0, 0. So this would give us n ln 2n minus n ln 2n minus 0, which is 0. And similarly, I would have the same thing for plus n mu 0 b. On the other hand, for E prime E is equal to 0 or E prime is equal to 0, I would have ln omega E is equal to n ln 2n minus capital N over 2 ln n minus capital N over 2 ln n. So that would make minus n ln n. So n ln 2n minus n ln n, that would give us n ln 2. So we see that if we plot this here, ln omega E as a function of energy, first of all, it has to be 0 at minus n mu 0 b and plus n mu 0 b, and then it has to be n ln 2 at 0, so n ln 2 at 0, and it has to be symmetric. So we find that the number of accessible states should be decreasing as we go from 0 to plus n ln mu 0 b and minus n ln mu 0 b. So we should get this look more like symmetric here. Okay, so that's basically how the plot will approximately look like. Okay, so we have done quite a bit of algebra for a capital N spin system where the total energy is minus n prime mu 0 b. First, we want to know the number of accessible states for an energy interval e to e plus delta e. Now, For a given n value and for that is corresponding to an energy value, the number of accessible states is the number of combinations of capital N objects taken n at a time. Now, for an energy interval delta E, we have to know how many possible different n values we can give, and because the energy is increasing in units of 2 mu 0 b as we change the n value, if we divide our energy interval by 2 mu 0 b, we find the number of different n values we can have in order to have the energy vary between E to E plus delta E. So the number of accessible states is capital N factorial over n factorial, capital N minus n factorial. So we're neglecting the change in the combinations as n is changing by a small amount, multiplied by the number of different n values, delta E divided by 2 mu 0 b. So for each n value, we have these combinations of capital N objects taken n at a time, and so we repeat this several times. So as we this is our approximation. Delta E is chosen small enough that the variation in energy does not cause an appreciable change in n values. So then we take the natural logarithm of this expression. Delta E divided by 2 mu 0 b was a small number. Its natural logarithm is also going to be even smaller. So it has to be not so many n values in this range. So we will end up neglecting that part. And by defining E prime as E divided by mu 0 b and performing the algebra, we see that to a good approximation, we can neglect the last term and write the number of accessible states this way, and we then observe that it has to be symmetric, and then we find that for a minimum energy and maximum energy requirement on the spin system, there is the number of accessible states natural logarithm becomes 0. So because the number of accessible states would be 1 if you have all spins pointing up or all spins pointing down, then it has a maximum for 0 energy at capital N ln 2. So it will look like a symmetric plot that starts from capital N ln 2 and decreases to 0 at the extremum energy values, as you can see in this plot that I have drawn here.